When we discussed the grain sizes and grain size distributions, we talked about sieve analysis, which was the method to determine the grain size distribution on the coarse side. But for the fine soils, we didn't talk about how to determine the grain size distributions. So in this lecture, we are going to do that. And the way to do that is, of course, theoretically, you can just look at the particles with a microscope and measure their sizes. However, when you have a fine soil, you have millions of particles in it. So it's not practically possible to do that. So instead, what we have is called the sedimentation test or analysis. And the idea in sedimentation is simply, if you jump off from the top of a skyscraper or an airplane, you are going to die. However, if an ant jumps out of an airplane, it is not going to die, it is going to survive. The reason for that is not because ant is sturdy. If you were the size of an ant and you jumped out of an airplane, you would still survive. And it has to do with what's called terminal velocity. So if an object is falling through a fluid, in this case, in this example's case, it was air, but it can be any fluid. So it is going to be under the action of its weight, and it is going to be diverting the fluid flow around itself, which actually will cause some sort of drag. So and the drag force is related to area of the object and velocity of the object, and also density of the object. Whereas weight is related to volume of the object. Actually, sorry, density should be here. So area is proportional to the size of the object squared, volume is proportional to the size of the object cubed. So if you have an object falling slowly, weight will be larger, so it will accelerate as it falls down. But as it accelerates, the drag force increases, and there will be a velocity called the terminal velocity, at which the drag force is equal to weight. So, by the way, this weight, because it is in a fluid, of course, this is going to be the submerged weight, or weight inside this fluid. So this is density minus density of fluid. So, of course, drag force is also related to viscosity of the fluid. So anyway, if you consider terminal velocities, then a larger object is going to have a much larger weight. So if you increase the size of the object, its volume, therefore its weight will increase a lot compared to its drag force. Therefore, a larger object, larger objects of the same density has larger terminal velocity. So we can use that basically if we can measure the terminal velocity of the grains, then we can relate that to their sizes. So this is called Stokes' law, by the way, and for a spherical object, what it boils down to is an equation like this. Actually, Stokes gives it in terms of terminal velocity is equal to a function of everything else, but here what we want is the diameter. So I'm going to convert it to that. Or actually, I can do that later. So let's do it this way. Terminal velocity here is going to be density of object or solid minus density of fluid, density of, let's call it solid, minus density of fluid, times g, this is gravity, gravitational acceleration, times d square over 18 times the viscosity. Here things have units because of this 18, so this is a theoretical relationship, but this 18 also has its own units. So the densities are in grams per cc. The velocity is centimeter per second. So the units are given in lab-sized scale, and density is in terms of millimeter. Viscosity is in terms of millipascal times second, and gravity is given as centimeter per second square. So this mu is the viscosity. So from here you can, if you need pull out, you can pull out the diameter and relate the velocity to the diameter. So, but we need our objects to come up to the terminal velocity very quickly. For that purpose, what we use is a suspension, because a liquid, in a liquid, objects come to their terminal velocities Sinking objects reach their terminal velocity very quickly. So in movies, when they shoot bullets into the water, into sea, you see bullets zip and then they quickly slow down. So like that here, if I throw my soil grains into water, they will instantly reach their terminal velocity because their terminal velocity is going to be very low. By the way, just a little reminder here, gravity, because everybody is used to taking 9.8 or 9.81 for gravity, remember that this is centimeter per second square, so it is 980. So let's consider a suspension. A suspension means immiscible or non-solvable grains that are mixed with a fluid. So I'm going to have my suspension here. In a column, and in that I'm going to have my grains homogeneously distributed over the height of the suspension. So here are my grains. These are the largest grains. So just to be able to distinguish them, I'm going to put smaller grains with another color and to a little bit to the side. So the experiment is going to run vertically. So I don't need to think about homogeneity in the horizontal direction here. So this is the initial state of my suspension. And then I'm going to move forward in time as the grains sink. Let's see what happens. So the red grains, the smallest grains, will sink the slowest. So let's move the time forward so that each red grain has moved just by one step down, and each green grain goes twice as fast. So let's make it like this, and each orange grain, let's assume, goes 3 times as fast. So I already have 3 of the orange grains down there. And then if I move the time forward a little more, now I have the red grains move some more. The green grains have sunk again twice the distance, and the orange grains have all sunk down. So this is the way it will go, provided the grains aren't interacting with each other. So if you have few enough grains, if you have too many grains, then they will they will bump into each other, they will prohibit each other's movement and so on. So we don't have that here. Okay, how are we going to distinguish between these? What we do is we take a snapshot. So let's say our snapshot or our sampling location is here. Now, if I, over time, if I keep going here and measuring how much how much grains are there, how much soil is in my suspension at this location, initially I have all the soil, so that is 100%. And gradually I'm losing the coarser bits. So this is like finer portion remaining from this particular size. And then again, finer portion, also known as percent finer than this size. And here I'm going to have my height, and I can calculate simply the velocity is going to be height over time. So time is 0, and then this way time axis goes. So, and if you want, you can imagine one more suspension where even the red grains have fallen off away from the sample space. So one challenge here is to relate, to figure out the percentage of grains remaining in there. So how can we do this? If you consider grains themselves are heavier than water, that's why they are sinking, but they are occupying the same space. So the overall average density relates to the percentage of the soil remaining in the suspension at that location, which is equivalent to percent finer, because the coarse grains sink first. So what remains are the finer grains. So how do we formulate this though? It is not easy, but actually it is, you can do it based simply on high school physics, but it might be a little complicated. So basically, if you think about it, initially the density of suspension is so let's say density of suspension at 100% is it's going to be the total mass divided by the total volume. So the total mass has the dry mass of solids, plus your mass of water, and mass of water is going to be volume of water times density of water. How much is the volume of water? It's going to be volume of suspension minus the volume of solids times density of water. Divide that by volume of suspension. And then starting from here, as you go towards a percentage of your soils remaining in the suspension, what will go down is this mass of solids. Instead of the total mass of solids, you are going to have a percentage of the mass of solids. So we can very simply figure this out if we rework what's going on here. If we open up this parenthesis, separate this fraction, what you can have is mass of solids divided by volume of suspension times, here you have volume of suspension divided by volume of suspension times density of water. So I'm going to, or let's call it not water, but let's call it density of fluid. So you have density of fluid. I'm going to send that to the other side. Density of suspension minus density of fluid. And here I'm going to have 1 from this, and I have mass of solids divided by density of solids and divided by volume of suspension as well. So I get just density of fluid divided by density of solids. So that is going to be 1 minus 1 over GS. So basically I can write it like this, or this parenthesis is also going to be, I like it better if, sorry, this is not 1 minus 1 over GS, this is because I have density of fluid here. Let's convert that into, again, back to densities. So it is going to be so this is going to be 1 minus density of fluid divided by density of suspension. And you can work that a bit more into actually, wait, you don't need to work that a bit more. What you need to consider is now, if this is, actually, let me rewrite it over to the other page so that I can carry over the calculations. Density of suspension minus density of fluid is equal to mass of solids over volume of suspension, 1 minus density of fluids over density of solids. So now I said this is the initial density of suspension, and if this is the 100% density of suspension, then this is the entire solids. But if I have a fraction of the solids, I have a fraction of the I have the density of suspension accordingly as well. So times percent finer comes here. So based on that, you can figure out simply the percent finer out of here. So the percent finer then becomes density of solids over density of solids minus density of fluids, the suspension over mass of solids, density of suspension minus density of fluids. Of course, times 100% to make it percentile. So the reason I avoided density of water here and I replaced it with density of fluids is because in order to do this test, you have to make sure the grains don't stick together. So you add 5 grams of sodium hexametaphosphate. It looks like this in chemical formula. Sodium hexametaphosphate into about 50 grams of soil and about 1 liter water. So this will be your suspension, or actually you try to make the suspension 1 liter. So this deflocculating agent, it is basically the main ingredient of Calgon or similar dishwashing detergents. So it prevents to prevent grains sticking together and sinking faster as larger grains. So what that means is now you have a solution. This is not pure water. This is water with 5 grams per liter of this sodium hexametaphosphate. So density of fluid is density of solution at the testing temperature. Because the density of water, therefore density of this solution will also be changing with temperature. So having that as well, the concept here comes down to this. You can relate terminal velocity to size, and to get terminal velocity, what you do is measure the or know the height of your measurement and measure the time. So time measurement relates to diameter of the grains, and here what we demonstrate is density of suspension relates to percent finer. So this means if I make my suspension column and I measure the density of suspension at regular time intervals, every time will correspond to a different diameter, and I will be measuring through the density, I will be measuring its percent finer. But you might have noticed we already need a bunch of different additional measurements. So also measure temperature, specific gravity of solids. Specific gravity of solids doesn't change obviously, but temperature may change over the experiment, so you want to measure that as well. But you have to, or you should aim to keep the temperature constant as well. So anyway, how do we do this then? Because, okay, measuring the time is easy. You just get a watch. Measuring the height of sinking is easy. Height of fall is easy because you can just measure it with a ruler. What about density of suspension then? There are a couple of ways. One of them is using a pipette to withdraw 10 cc's of suspension there, but that disturbs the suspension a lot, and continuing the test becomes difficult afterwards. So instead, what we use is a hydrometer. A hydrometer is a device. So people commonly calls this a hydrometer test. It is, and it is for determining the grain size distribution. Hydrometer doesn't determine grain size distribution. It doesn't determine grain size at all. It's a device for measuring fluid density. And the way it works is it's basically something like this. It has a stem, it has a long stem, and then it has a bulb section like this. And inside the bulb you have a weight, so that when you put it in a liquid, the center of gravity is lower than the centroid. That makes it always point downwards like this. And most of the volume is in the bulb section. And you have a constant cross section up here. So if you, and its density its density is slightly less than the density of water. So actually it is like 0.99 something. That means if you put it in water, if you put it in pure water, it is going to sink to something like this. Your water level will be, let's say, here. So only a tiny bit of it is going to be sticking out. If you put it into a denser fluid, more of it will stick out because its weight must be supported by the weight of the fluid that will occupy the volume under the fluid surface. So if you put it in a denser fluid, it will stick out like this. And because the cross section of this stem is constant, what you can simply do is you can have gradations here and have them calibrated like this. So then it becomes very straightforward. You just dip this into, or you leave this to equilibrate inside your suspension, and wherever your water surface lands or suspension surface lands, that will be your density of suspension. So, well, that sounds nice. So basically, what you have is your device like this. But then it poses its own trouble. The first problem here is if you look really closely to any measurement you take, what you are going to see is something like this. So you have the stem. Let's say you have gradations like this. And then the water surface or the suspension surface. And this is made of glass. So the suspension surface, let's say it is here. But because of contact angle and surface tension, what you are going to have is going to be something like this. So if you look at the water that you fill into your glass, for example, if you look carefully around the surface, the water looks like it wants to climb up the glass. That's because for glass surfaces, water is more wetting compared to air. Water is the wetting phase. So here as well, this is glass, so water wants to go up underneath the air in the contact. So that is not the real water surface you have. The real water surface is here. So this is your real water surface. Okay, so let's read at that level. That's fine, but the problem there is, remember, this is suspension of a fine-grained soil. So essentially it is mud. So what you have is this. So that means sometimes you cannot see through this, through the mud. So the way to fix that is always read here. So read above the meniscus always. Let's call that RM. And here, let's call this location the true reading. So this is reading due to change reading due to meniscus, reading above the meniscus. Your true reading is down here. Thankfully, you always have the same difference. So let's call that CM. And if you read that once through not so much mud, maybe through just water or through just, because sodium hexametaphosphate might change the surface tension properties, through sodium hexametaphosphate solution, you can read this meniscus correction. And then your true reading will be your reading that you can see plus CM. Why is it plus? By the way, it's not the distance, it is in terms of density. CM is in terms of density, because the scale goes larger as you go down on the stem of the hydrometer. So that's why you need to add this correction to it. So your readings must be corrected as such. Another problem, another challenge the hydrometer poses is, as the test progresses, at the beginning, you are going to have a high density. So the suspension surface will be here as you start the test. As time passes, it will sink more because grains are sinking. As the grains sink, your suspension is getting lighter. That means for your next measurement time, your hydrometer goes more down. So your height of measurement changes. So you have to consider that. And for that, you can you can come up with a calibration scheme. So basically, uh, the density measurement happens across the volume of the bulb. So it is like an average density measurement over the bulb volume. But you can consider it's that it's centroid. So here is the measurement location. So this is the centroid. Assume centroid is the location of measurement, and let's call this H1 and this is R1, and let's call another location up here H2, and this is, let's say, R2. So you can just measure these by a ruler outside the suspension, and then you can write a formula that will make linear interpolation between these, because remember, this scale is linear here. So you can just make a linear interpolation formulation here for whatever R you have in between. You can calculate the H. Now there is more. And that more is when you start the test. Okay, you can put this device into your suspension, but we don't leave the hydrometer in for more than 2 minutes. The reason for that is because the sinking grains will stick to the hydrometer and accumulate on the hydrometer, and therefore they will make it heavier, and the hydrometer will sink more, and it will disturb the measurement. So we don't want that. So we have to somehow deal with that, because now you have this problem. You have to, for every measurement, you have to slowly lower the hydrometer into the suspension, which is possible, you can do that. But that means as the hydrometer occupies volume, it's going to stretch out, it's going to elongate the fluid around it. The fluid level will rise up. So the original level might have been here in this little figure, but once you put the hydrometer in, the fluid level has gone up a little bit. How much does it go up? It goes up by the volume of the hydrometer divided by area of this suspension. So this elongation happens that much. But my point of measurement is halfway through that volume. So I need to consider just half of that. So this is the volume of hydrometer divided by area of suspension. And I want to consider half of that, and I want to subtract half of that from the heights I measure here, because while the grains have been sinking, we didn't have the hydrometer in, so the height was shorter. Once I put the hydrometer to measure, I'm elongating the height. So that is a lot of considerations, but you can, if you merge all of them, your true height of fall is going to end up. First, let's write the interpolation equation. So this is the slope here. Times, so you can either do this H1 and here as well R1, or H2 and R2, that by changing the sign. Yeah, you need to make this minus in that case, but anyway, so you can do it either way. Instead of R, I'm going to put Rm plus Cm minus R1. So this is my meniscus correction. This bit altogether is my linear interpolation of height. This is meniscus correction, and this is water elongation. Volume of hydrometer divided by 2 times area of the suspension. So now I have the height. I can plug that height into my Stokes law, which I have written earlier, but I'm going to rewrite it in the form that is more useful. And here is your terminal velocity. So if I plug that height in here, I get the diameter as a function of time, but also the density of suspension. The measurement of the density of suspension also affects the height. And I already wrote the percent finer as here. So that way, for every hydrometer reading, at a different time, gives a point on the grain size distribution. Okay, that's basically it. This is like one of the most complicated tests we have as far as the calculations are concerned in this chapter. And wait, there is more. So remember that, keep in mind that let me carry that over as well. Percent finer is density of suspension, sorry, density of solids over density of solids minus density of fluid, volume of suspension over mass of solids, density of suspension minus density of fluid times 100%. Now, it's important to remember that this mass of solids is mass that went into the test, into the suspension. And this is percent finer, percentage out of the mass that went into the test. Well, obviously, why am I writing this? The reason for me writing this is because you have to consider this not in vacuum, but you have to consider this together with the sieve analysis. So imagine you have 100 grams of soil that you put into the sieve, and then 40 grams of this is fine and 60 grams is coarse. Then what you have to do is you take this 40 grams, put it into a hydrometer test or sedimentation test. Then for any given time, let's say you calculated percent finer is for a certain time, percent finer is 70%. Now you have to remember that this 70%, as an example, so this 70% is 70% of 40. So therefore this is 40%, this is 60%. So this is 70% of the 40% that went into this test. So therefore that is 28% in reality. So the formula will give you that calculation from the hydrometer test will give you 70%, but you have to multiply that with the percentage that went into the test. And I'm not calling that the fine fraction either, because sometimes in order to capture fine particles better, because some of the flocculations, maybe some of the clumps didn't break well, so people instead of putting just the fine fraction into the hydrometer, they put the fine fraction plus the fine sand fraction as well. So instead of everything below 75 microns, sometimes people put everything below 400 microns, for example. So then the percentage that went into the test would be the percentage that's finer than the 400 microns. So whatever that percentage is, you have to multiply this percentage that went into the test. You have to multiply this by every percentage you calculate from the sedimentation formulation. Okay, I know this one was very complex, but I'm sure you are going to get the hang of it once you also do the lab report for it.